I should be able to do that. Let me do it like this. Hey Billy, how's it going?
How you doing, Professor?
All right. Okay, so we'll get started in a minute or two. Any questions or about anything, or any homework problems or anything you want to discuss? Okay, we'll give people a few more minutes. So anybody watch the debates last night?
Yeah, I watched it.
What were your thoughts?
It was interesting. It was definitely interesting.
I've seen probably.
You guys talking about last night?
Yeah.
Yeah, I've seen probably about 14 or 13 presidential debates, and that was probably the strangest I've ever seen. Really weird.
Chris Wallace at the end. No, we're done. We're done. To be continued.
That was crazy. All right, so we'll get started in a minute or two. But any questions on anything before we get started from past homeworks or anything like that? Any issues with Verify? I know there's one person that had a really weird issue, and they were the only one, so I didn't mention it to the class, but anything goes on, just keep me in the loop. Verify never fails to surprise us. Okay, so this week's material is probably more challenging than what we've done in the past, and we're going to talk about a topic today called implicit differentiation. And sometimes I'll just abbreviate it with ID, the same way that I abbreviated chain rule with CR, just to keep things short. So one question is, when do we use implicit differentiation? What is it good for? And the purpose of implicit differentiation is it lets us take derivatives of equations involving functions of x. Okay, so this is something a little different now. So what it lets us do is it lets us take derivatives involving functions of our independent variable. And so to kind of give you an example of what I'm talking about here, so let's say we're going to have some equation, maybe it looks like this. We'll say 2x to the 7th minus 5y squared is equal to 12. And you notice you have two variables running around here, okay? You have x, which is generally thought of as the independent variable. Okay? But you have y, which is a dependent variable. In other words, it's a function of x. Okay, we're thinking of y as depending on x, right? And actually, I want to say dependent. Whoops. Yeah, scratch that. And so what makes this problem new is that we have not only functions of independent variables, which I could take the derivative with respect to x, but I have functions of the dependent variable, which I really don't know how to take the derivative with respect to y. Okay, so the point here is that I want to take the derivative for this sort of equation. I want to take the derivative with respect to x, and I want to solve for dy dx. That's our goal. So this is a new sort of scenario, and this is why we introduced this technique called implicit differentiation. Now, before I get into implicit differentiation, I want to revisit the chain rule, because it turns out that implicit differentiation is really just a special case of the chain rule. Okay? So if you look at this problem, the hard part of this problem is taking the derivative with respect to x of y squared. And what I'm going to do is I'm going to think about this as the derivative with respect to x, and my outside function is going to be the square function, and my inside function is going to be y of x. So this is my outside function, and this is my inside function. Okay? And what I'm going to do is I'm going to present the chain rule in a different way, okay? So here's how we're going to start thinking about the chain rule. We're going to think of it as d dx of f of blob. I'm going to think of f as my outside function, and blob as my inside function. And we're going to say this is equal to the derivative of f of blob with respect to blob times the derivative of blob with respect to x. Okay? So if I apply this sort of way of thinking about it, which seems a little weird in the beginning, okay, but just kind of follow me for a second, all right? If I go ahead and try to apply this, okay, I'm going to think of blob as y, right? The blob is the inside. This is f of y. Everybody agrees here, okay? This function f is the outside function. So this is d blob, which here is y, times y squared, times the derivative of blob, which is y, with respect to x. Okay? Again, outside function, inside function. So this tells me take the derivative of the outside function with respect to the inside function, which I'm calling blob, okay? Then take the derivative of blob, my inside function, with respect to x. And this is easy to do, right? Derivative of y squared with respect to y is just 2y, right? And the derivative of y with respect to x is just y prime. Okay? So sometimes when people think about the chain rule, they write it this way, and here's how they think about it, okay? Let me show you another way of thinking about it if you don't like the blob picture. So I'm taking the derivative of a composition of functions. And so sometimes people write it like this. And here's how they think about it. They think of the outside function as the mother. And they think of the inside function as the child. And what they say is take the derivative of the mother and leave the baby alone. Okay? That's what I'm doing here. I'm taking the derivative of the mother, the outside function, with respect to the baby. That's what it means by leave the baby alone. Then multiply it by the derivative of the baby. Okay? So there's a lot of different ways of looking at this, okay? If you don't like any of these, I'll show you a third way that's even easier. Okay? This is just equal to the f dy times y prime. So all of these ways are equivalent ways of thinking about the chain rule, okay? This is more specific to what we're doing. So this is a little more tailored towards implicit differentiation. But all of these ways of thinking about the chain rule are all kind of the same. All right? And I'm going to use 3. This is what I'm going to use today. Okay? All right, before we plunge in, do we have any questions first? All right, well, buckle up. We're going to get started. And I'm going to go to, if you guys don't mind, I'm going to go to the practice problems that are posted for this chapter. And we're going to work through a few examples. All right? And they're going to go, generally speaking, in order of increasing difficulty. This is our first problem. So we're always going to be taking the derivative with respect to x here. All right? Give me a second here. Zoom sometimes causes stuff to freeze up. It's a real pain. Let me see if I can get out of here really quick. Okay, I can. That's good. There we go. Sorry about that. Okay, so what I'm always going to do is I want to find y prime, which is dy dx, right? I'm going to start off by taking the derivative of both sides with respect to x. BS means both sides, by the way. Okay? So d dx of 5x minus 7y plus 12. And of course, the derivative of 0 is 0, but, you know, just to be a good citizen, we'll put that in. And now I'm going to apply my derivative rules for forms, okay? I'm always going to start off thinking about forms. Whenever you're totally lost, you ask yourself, what form am I taking the derivative of? So here, am I taking the derivative of a sum or a difference? Yeah, right? So I'm going to go ahead and use the addition rule. So the addition rule says it's going to be 5. I'm going to use the fact that I can distribute the d dx, and I can factor out a constant multiple, right? Okay? And really there's nothing to do here, right? Because the derivative of x with respect to x, is 1. And the derivative of y with respect to x is just y prime, right? So not a big deal. Of course, that's 0. So we get 5 times 1 minus 7y prime is equal to 0. And now I'm just going to solve for y prime. So I do my little algebra magic, right? 5 is equal to 7y prime. Even I can do that one. Y prime is 5 over 7. And we're good. Okay? Questions? And you might say, so easy. But of course it's not that easy, right? Kind of like a video game. We just keep on going up in level of difficulty. So let's look at the next one. Always start off the same, right? Take the derivative of both sides with respect to x. dx of both sides. And now we're going to apply our derivative rules, right? So here I have a derivative of a difference, and each term is a scalar multiple, and here I have a derivative of a constant term, right? So now we're going to apply our derivative rules. So whenever I have a sum, I always distribute the derivative operator, and I'm going to factor out these constant multiples, right? Okay? And of course, the first term is trivial, right? I mean, derivative of x squared with respect to x is just 2x, right? Times 3 minus 2 times. Now, how do we take the derivative of y cubed with respect to x? So let's look at this off to the side, okay? Let's see, we'll put this over here. So the way that we do this is we take the derivative with respect to y first, right? So this is dy of y cubed. Okay? And then we multiply it by y prime. Okay? Take the derivative of the function with respect to y. That's this part here. And then we always multiply by the derivative of y with respect to x. So notice what we're doing is we're treating this as if the variable is y originally, right? I'm pretending the x is not there. I'm pretending that the d dx is really the d dy, and then I'm kind of adding this fudge factor at the end to take into account that I'm really not taking the derivative with respect to y. I'm really taking it with respect to x. Okay? And if all of this looks a little bit like black magic, okay, what I want you to notice is that if you write it like this, you can kind of see why this rule works, okay? And again, this is not a proof, okay? But you can see that these guys kind of cancel in a sense, right? And so this is one way of rationalizing, although it's not a proof. But it's one way of kind of rationalizing what's going on. And so I can take the derivative of y cubed with respect to y, right? I'm going to get 3y squared. And then I'm always going to tack on that y prime. Okay? Does that look good? Is everyone okay with that so far? Can I get an amen? Are you guys awake? Hold on. Okay. You guys good?
Yes.
So does this implicit differentiation, does it seem really crazy, or does that sound like it makes sense what we're doing? Let me put it another way. Are you okay using this formula right here? This is how we really want to think about it, this formula right here. Okay? Everyone's okay with this formula? Okay? So you pretend like you're taking the derivative with respect to y originally, and then you always multiply it by y prime. So one way of saying this in words is we pretend, let me minimize this for a second. Oh, come on. So what we do is we pretend, I'm going to pretend like my pen's working here in a second. Oh, come on. So what we do is we pretend we're taking the derivative with respect to y. That's this part right here, and then we multiply by y prime. Okay? But I'm not done. I have to solve for y prime, right? So we're almost there. We're on the 1 yard line. So now I have to solve for y prime. And I can do that, right? Just bring all the terms that have y prime over to one side. So 6x is equal to 6y squared y prime. And then just go ahead and divide by everything that's multiplying y prime. And be done. And that, ladies and gents, is our answer. Okay? Any questions that we have? All right, good. So let's sally forth and look at the next one. The next two problems are the sort of problems that you'll see on the exam and most likely on the final. Even though I don't make up the final or the exam, I can tell you from past experience, this is the level of difficulty you'll have to deal with. Okay, so let's start off. Take the derivative of both sides with respect to x. Okay. It's always a good idea when you're working these problems to try to write everything out. It's very easy to make a stupid algebraic error, a simple algebraic error. And if you write it out, at least I'll understand that you know what you're doing. And when you go back to check over your work, which I strongly recommend you do, it will make it a lot easier. Okay, you'll be able to actually understand what you did. Okay, I'm going to go ahead and distribute. And I'm going to take out constant multiples, right? So I'm going to get 6 dy dx minus 3 dx dx plus 7. And now here I got a mess, right? X cubed y squared. And of course, on the right-hand side, the derivative of 20 is 0, right? So I get minus d dx of y cubed. All right? And so everything in this problem is relatively straightforward with the exception of these two terms. I'm going to have to use implicit differentiation on both of them because I have functions of y, right? That's when we know we do implicit differentiation. So of course this is y prime, so I get 6 y prime minus derivative of x with respect to x is just 1, okay, plus, how am I going to take the derivative of x cubed y squared? Anybody? Okay, so let me ask you this. What form do I have here? Am I adding two things, subtracting, taking a multiple of a function, a product of a function, a quotient of a function of a function? What do I have here? What am I doing? Okay, here's another way to think about this. If you were computing this, what is the last operation that you would do?
The addition and subtraction.
No, I'm referring to x cubed y squared. Okay, if I just looked at this one thing here, what is the last?
Into the multiplication.
It's going to be multiplication, right? It's x cubed times y squared. So here I'm going to have to use the product rule. I have a product. And so the product rule tells me it's the derivative of the first factor, right, times the second function, I leave that alone, plus x cubed times the derivative of the second function. Okay? And here, I'm going to use implicit differentiation on the right-hand side, right? I'm going to take the derivative with respect to y. So if I take the derivative of y cubed with respect to y, what do I get? If you took the derivative of x cubed with respect to x, what would you get? Well, you would get 3x squared, right? Well, there's nothing magical about the variable x. So if I take the derivative of y cubed with respect to y, I'm going to get 3y squared. But again, I remember with the chain rule, with the implicit differentiation, again, special case of the chain rule, I'm always going to multiply by y prime. Okay? And so the last thing we have to do now is evaluate the derivatives in this sum. Okay, so if we do that, I'm going to get 6y prime minus 3 plus 7. And this is going to be 3x squared, the first term, right? Times y squared plus x cubed. And again, I remember how I take the derivative of y squared with respect to x. First, I pretend like I'm taking the derivative with respect to y, right? So I get 2y. But then I say, oh wait, it wasn't with respect to y, it was with respect to x. And my little fudge factor here is y prime. Okay. And finally, I have this minus 3y squared y prime. So let's clean this up a little bit, okay? Let's kind of get this a little better organized here. So this will be 6y prime minus 3. I'm going to distribute my 7. And I'll get 21x squared y squared plus 14x cubed y times y prime is equal to minus 3y squared y prime. Does that look okay? Does that seem all right? Okay, now your mission, should you care to accept it, is to solve for y prime, which means I need to get all the y prime terms over to one side. So these are all my terms that have y prime, and I'm going to get them all over to one side. It doesn't really matter how you do it. I'm going to bring them over to the left-hand side because I want to solve for y prime anyhow. Okay, so I'll leave these two terms here, and I'm going to bring these two terms over to the right-hand side. So 16y prime plus 14 y x cubed y prime plus 3y squared y prime. I'm going to add a positive 3y squared y prime, right? And now when I bring these two terms over, I'm going to get 3 minus 21 x squared y squared. Does that look okay? I didn't goof anything up, right? I think I did that okay. Now, why did I do that? Well, I cold-bloodedly set that up because what do I want to do now? I want to take a common factor of y prime out, right? Notice that every term has a factor of y prime. So I can factor out y prime. So I'll get 6 plus, if I take the y prime out, I just have 14yx cubed, right? Plus 3y squared. Okay? And the whole thing, the whole quantity is times y prime. So just factor out a y prime. And that always works, by the way. You can always do this with implicit differentiation. It always works out that way. There'll be a linear factor of y prime that you can factor out. And now for the pièce de résistance, I just divide by this whole thing multiplying y prime, right? And of course, again, I cold-bloodedly set that up so those guys will cancel. And there's my answer in all of its savage splendor. And we could have seen that from the very beginning. That's obvious, right? Heck, it is, right? Very, very, very unobvious. So the moral of the story is you have to be really careful because there's no way that you could tell, and there's no way that I could tell you off the top of my head just by looking at it what the answer is, okay? And you're not going to be able to tell if you make a mistake here or there, okay? It's not obvious at all what you should get. Notice all this algebra that we had to go through, right? So you want to take your time. Bookkeeping is really important in mathematics, okay? Want to make sure that we have some way to check our answer and to be able to get there without making mistakes, or at least minimizing. Okay, questions that we have on that? All right. The next one is really fun. You're going to like this, I think. Now, people sometimes ask me, what do you mean by a fun problem? And what I mean by a fun problem is it's one that really tests your understanding, right? It's one that if you're able to do it, you know you actually know it. You get a good feeling. So this here is a fun problem for sure. Because if you can do this, you really understand what you're doing. Okay, so again, our mission, should we decide to accept it, is to find y prime. Okay, same game. Let's go ahead and take the derivative with respect to x on both sides. Okay, I can factor out a 4 here, right? So 4 comes out, and that'll go to 0, and I'll be left with 4 times the derivative of 3x. I'm sorry, that's minus 7y, sorry. Drop my y there. Why? I don't know. There we are. Okay. Now, for the $10 million prize and the year's supply of turtle wax, how do I take the derivative of this guy right here? Okay, what is the form? What do I have? Am I adding two terms? Am I subtracting? Am I multiplying? Am I dividing? Am I taking a function of a function? What do I have here? Which one of those things do I have? Hopefully, you realize you have a composition, right? So this problem is going to be both chain rule and implicit differentiation, because this is how we deal with functions of functions. So I want to look at this function here. So here's how I'm going to think about this, okay? I'm going to think of my inside function. My outside function is to the 5th power, right? My inside function I'm going to call blob. And so now I'm going to use this second way of thinking about the chain rule, right? I'm going to say, if I take the derivative of blob to the 5th with respect to blob, and multiply it by the derivative of that inside function blob with respect to x, I'll get my answer. And this part's easy, right? The derivative of blob to the 5th with respect to blob is just 5 times blob to the 4th power. Okay? This is the power rule, right? The variable I'm taking the derivative with respect to is the variable in the base. And now it's going to be derivative of blob with respect to x. So let's use this approach, okay? So here's what we have. We have 4 times d dx of 4x minus 7y to the 5th is equal to 0. And so I'm going to think of this inside function right here, right? This function right here, I'm going to think of this as the blob. Okay, this inside function. Why is that not writing? That's weird. So in any case, it's going to be 4 times 5 blob to the 5th power, which here is going to be 4x minus 7y to the 4th. This is my blob, times the derivative of the blob, the inside function, and that's it. Okay? So hopefully you make the connection between these two things that I've written here. Okay? This part is this, and this part is that. Okay? And so now I can easily take the derivative of this last part, right? The derivative of the blob is always easy to do. So now I'm going to get 20 times 4x minus 7y to the 4th times 4 minus 7y prime is equal to 0. Okay? And if I wanted to, I could go ahead and distribute, but I can also realize that I can get rid of this entire quantity here just by multiplying by both sides. Notice that there's a little caveat here. I can't divide by 0, right? So we can never have 4x minus 7y being equal to 0. That's a little caveat we have here. But as long as that's true, I can go ahead and divide, and I get 4 minus 7y prime is equal to 0. And even I can do that. And there he is. Okay. So what do we think? easy, hard? What do you think, Jacob? On a scale from 1 to 10. 10 is really hard, 1 is super easy.
Probably around a 6 or so.
Okay. So usually most people say 6 or 7-ish. Okay. So here's the thing. I'm going to work one more problem. But again, I want to reemphasize this fact, okay? It's easy to watch somebody do something and be able to follow them and understand what they're doing. It's different for you to be able to do it, okay? So I strongly recommend that either tonight or tomorrow you sit down and at least work some of the problems in this sheet, if not the homeworks also, okay? This is one that you don't want to get behind on, trust me. 5 is good. I like 5 too. So, getting good at mathematics is like how you play at Carnegie Hall, right? Practice, practice, practice. Okay, so take the derivative of both sides with respect to x. I'm going to go ahead and I'm going to distribute. And take out my factors here, right? My scalar factors. Okay. How do I deal with the derivative of 1 over x? With respect to x. How am I going to do that? Well, hopefully you recognize that this is a reciprocal power. So I'm going to have to want to write this as x to the minus 1. And so using that insight, I'm going to want to write this as y to the minus 1. Okay? So I'm going to take d dx of x to the minus 1 minus 3 d dx of y to the minus 1. Okay? And the first term is a straightforward power rule, right? This is the derivative of x to the n. So I know that when I take the derivative, I'm going to bring down the exponent, which is a minus 1, and I'm going to reduce the exponent by 1. Okay? And the thing to remember, notice that now this looks like a power rule problem also, right, with the y to the minus 1, but it's not. It's an implicit differentiation. So the first thing I'm going to do is I'm going to take the derivative with respect to y, right? I'm going to pretend like I'm not taking the derivative with respect to x. But then I'm going to multiply it by y prime. So going from here to here, this is implicit differentiation. And this is just the power rule, right? This is minus 1. I bring the exponent down the same way I did with the x, right? And this is y to the minus 2. Okay. Times y prime minus 3 minus 5 x to the minus 2 is equal to 0. You really want to take your time. The algebra is very easy to make a simple error here, okay? And now I'm going to kind of clean this up, okay? I'm going to go ahead and clean up my coefficients here, and I'm going to make my negative exponents positive, right? So this becomes minus 5 over x squared. The negative 3 and the negative 1 will be a positive 3. And I bring the negative squared down here to the bottom. And I have this. Okay? And now for the coup de grace. as they say, I'm going to solve for y prime. So I'll bring this little fellow over here. And so now I have to bring this term over to here, and whenever I want to get rid of a multiple, right, this thing is multiplying y prime, I multiply by its reciprocal, right? And of course it's an equation, so I got to do the same to both sides. Okay. Whoops, that's a 3, not a 2. There we go. Right. And of course I cold-bloodedly did that because I can cancel those out. And when all the mathematical smoke clears, you get 5y squared over 3x squared. And that, my friends, is your final answer. All right. Now, let's look at problem 6, okay? This is a really good problem, actually. This is a problem that would probably be difficult for most people to do just cold. And I'm just going to talk about setting it up, okay? So, we have the equation of motion for the tip of a propeller. And what they want you to do is they want you to find the equation of the tangent line. So I'm going to go back to something I've already told you guys. So this is my propeller, right? It's going around. And if all of a sudden the tip were to break off, remember what we said, that that if you're going in circular motion and all of a sudden something breaks off, it goes to a tangent line, right? So this is the motion. So if you're swinging something around and the rope breaks, right, the thing doesn't go flying off. It keeps going along the tangent line, okay? So this is the line that we want. Okay? And we know what m is. M is going to be y prime at whatever our x value is. Okay, so let's go ahead and see how to do this. So if I want the equation of the line, and what they want the tangent line here, this is what happens when you're looking at motion, okay? I want the equation of the tangent line. I need the slope and a point. For any line, right? Not just a tangent line. Well, you're given the point is minus 4, 3. And you know that the slope of the tangent line is going to be y prime evaluated at the x coordinate that you're given. So what we really want to do is we want to find the equation for y prime and then plug y equal to minus 4 in there. So, again, slope means derivative, right? Y prime. So let's take the derivative of both sides. What, 25? Yeah. And so again, derivative of x squared is going to be 2x. And now I'm going to try this a little more quickly, okay? I'm taking the derivative of y squared with respect to x. So first I take the derivative of y squared with respect to y, which is 2y, and I multiply it by y prime, and I get 0. And when I solve for y prime, I'm going to get minus x over y. And the x coordinate and the y coordinate here I'm interested in is minus 4, 3. So the slope of my tangent line is going to be minus 4 over 3, or 4/3. And so now we're almost done, right? Y is equal to, well, let me do slope. Let me do slope intercept form, right? So m is equal to y minus y naught over x minus x naught. And again, x naught and y naught are the coordinates for this point. So 4/3 is equal to y minus 3 over x plus 4. And I'll leave that for you to solve for y. But that's how we set that up, okay? So the thing that a lot of students wouldn't know, but I did mention this before in class, is that when you have a particle exhibiting circular motion, if for some reason it ends up breaking off, that object ends up moving along the tangent line to that circle. Okay, that's a pretty good day. We got a lot in. Let's see. Questions that we have before we call it a day. Any questions on that? Okay, I'm going to go ahead. I'll post the video if you want to go back and look at it later on. And again, really try to work on the homeworks. If you have any questions, let me know. Because I think this one's going to be a little more challenging than the others. Okay, I will see you guys on Friday then. Thanks. Right, should be that.